Hey everybody. Today you can see the title on the screen. We're going to go through a full lesson on how to find the distance from a point to a line. As we work our way through today, I want to take a deep dive into all the theory that's involved with it and then give you a chance to be able to work through two examples, two problems for us to deal with. Okay, so we're talking distance from a point to a line. Here we go. So what you see on your screen right now, you've got two sets of axes. I want you to focus in on the one on the left. I've given you a very specific line in red, a vertical line, and I've given you a point, just a generic point in green. Let's call that generic point point P, so we can just use that name. I am asking you how far, so what is the distance from P to the line? Now, I suppose I should be very specific here and put arrows on to say that that goes on forever. How far is it from P to the line? And if you were to take out your ruler and try to measure that distance, I'm hoping that we get how we measure a distance from a point to a line. So let me put some specific values to it. Let's say that I said that this vertical line was at x equals 2. And I said that this generic point P was now a specific point. Since I'm in quadrant 3, maybe I happen to be at -5, -3. I don't know, something like that. If I was to ask you, how far is it from P to the line, I would hope that we would take a look at that and we would measure that in a horizontal way. What I mean by that is, if we were to measure, we would want to measure the distance that is perpendicular to that line. And we could take a look right now and say, well, it's going to take me 5 units to get to my y-axis, another 2 units to get to the line. Okay, the distance from P to the line, 7 units. For us to measure the distance from a point to a vertical line, pretty straightforward. How far is it from the point to the line? 7 units. Now, there is some theory involved in that. And what I mean by that is we do have to understand a couple little, or one big restriction. That when we measure a point to a line, what we really are looking for is the shortest distance. And the way I measure shortest distance is perpendicular. Now, just to deal with the case one more time, if you took a look on the right set of axes, I want you to imagine on the right set of axes, this time I give a horizontal line. I'll put my arrows on the end, and maybe my point P is still sitting at that same location, somewhere over here. If I asked you, how far is it from point P to that line, then I would hope that we would take a look at that and we would say, I want to measure in a perpendicular way. And so really what I'm looking for then is the length of that orange line segment. And I don't think that we need to go through and put on specific values to it, as long as we know we are measuring in a perpendicular way. Okay, why is that the case? Well, I want to jump into a different situation, but it's one that I think is going to highlight for us why we need to look at this perpendicular aspect. I want you to take a look at the diagram I've given you on the left now. And maybe this kind of gets you a little bit more. The fact that your line has a slope to it. It's not horizontal, it's not vertical, so it's leaning. It's got a slope to it. And if I was to ask you now, how far is point P to that line, I hope that you could see there are a lot of different lines that you could draw on. That is, you could sit and say, well, how far is it from point P to that line? And if we put on our horizontal line segment, well, then that might give us a different distance than our vertical line segment. And so which one of those distances are the case? Okay, to discuss that, I think we need to talk then about that shortest distance aspect. So let me get rid of both of those blue lines, and then we can take a look over on that right side. So I'm just going to get rid of both of those blue lines. And unfortunately, that meant that I got rid of part of my axes and my line segment, but for the most part, we're now good. Okay, if we were sitting in class right now, then I may be asking you, imagine that one of the walls of our classroom is the line. Here, I'll draw on one of our walls. And let's say that that happens to be the wall that has like the door through it. I happen to be standing somewhere over here. If I asked you, how far am I, a point, from the wall? Then we could take my position and we could measure it a number of different ways. Maybe we measure it over to this corner. Maybe we measure it to this corner. But if I asked you, no, how far am I from that wall? I would hope that we would all recognize we would be measuring the shortest distance to that wall. That what we actually do then is we measure it in a perpendicular way. So when we go back, and I get rid of my beautiful drawing on the right side, for us to come up with what is the distance to that slanted line, I now need to come up with, and I'm going to do my best to draw on, that perpendicular looking line. I need to come up with the length of the orange line segment. That is going to tell me how far I am from that line. That represents for us the shortest distance. So when you are asked to come up with the distance from a point to a line, then you're asked to come up with the shortest one, the direct one, the one that gets you there the fastest. And in all those cases, we're talking about a perpendicular distance. So what I want to do then is I want to spend the rest of today just going through two problems. How we can get the distance from a point to a line, and we can look at all of the little skills that are involved in coming up with that value. Okay, here we go. I want you to take a look on your screen right now, and you'll see that on that screen, we have one problem. Find the distance from point A, negative 6, 7, to the line y equals 2x minus 1. Okay, if I were sitting down to deal with this problem, I would 100% of the time draw a picture. So my suggestion to you, put on a quick sketch. Let's put on a quick set of axes, and the more accurate we can be, the better our diagram will be, the better our information will be, and therefore the better our outcome will be. What I'm saying is we could just throw on a sloppy line and say, hey, there's y equals 2x minus 1. Look, I was pretty accurate. It has a y-intercept of negative 1 and a slope of 2. Look, I'm rising to the right. Now, you might notice I don't really have a slope of 2. Like my slope looks closer to 1. I seem to have like the same horizontal distance as what I have as my vertical one. And that inaccuracy is going to mean that my potential solution isn't going to match my picture that much. Now, it doesn't mean that my picture isn't helpful. It is, but it could be more helpful. So, my suggestion to you, when you go through and you build your sketch, take your time. I'm looking at that line, y equals 2x minus 1, and I say, okay, I have a y-intercept of negative 1. If I now want to have a slope of 2, then that means I have to make sure that my line is steeper than 1. And so what I might do then is I might take out my straight edge after estimating those two values. And now what I'm going to do is I'm going to try to draw my line through those values. When I do that, I now have a more accurate sketch for my line. And therefore, any conclusion that I might end up getting afterwards is going to be more accurate. Okay, there's my line. Now I want to try to be as accurate as I can with my point. Well, negative 6, 7 means I have to go across 6 and up just a little bit more. Maybe there is my location of point A. And now what that question's asking me for is to come up with the perpendicular distance. So if I go to now try and draw on a perpendicular line segment, I'm not pulling out a protractor to do that. I'm just eyeballing it. But as I eyeball it, I want it to be, as much as I can, a perpendicular line segment. So I'm not now pulling out a protractor measuring. No, that means my sketch is too cumbersome. But I think if I just go on my eyes, then that's a pretty decent sketch. There's the situation that we've been asked to come up with. And you have been asked to come up with the length of the orange line segment. Okay, that's our job. Now, if you're looking for a challenge right away, then my suggestion to you would be pause the video and give it a shot. We'll come back and we'll see how well things go. Otherwise, you may want to kind of work together on this first one. Okay, what do I know in the problem? Well, first off, I know that the slope of that red line is 2. I can read it because it's in slope-intercept form. Well, if I also then know that my orange line has to be perpendicular to the red, then I know that any perpendicular slope to that has to be its negative reciprocal. So flip it, change the sign. Now, I am a big fan of trying to use as much notation and labels as possible. And so rather than just calling it a generic slope that's perpendicular, I'm going to actually use a line segment. I already have point A in green, but I don't have the other end point labeled. So I'm going to give it a label, and I'm going to call it B. That now allows me to state, rather than just a generic perpendicular, I can state that the slope and use subscript of AB is negative 1/2. Okay, there we go. Well, if I was able to go through now and figure out the length of AB, then I would need to know the position of both of those endpoints. I do know the position of A. I don't know the position of B. And so my job is to figure out what's the coordinates of point B. I do notice that point B is at the point of intersection between my orange and red lines. And hopefully we remember that to find the point of intersection means to solve a system. To solve a system means I need my two equations. Well, right now, I have equation 1. It was given to me, my red line. I don't have equation 2, my orange line. I need to build it. There's my whole process. And we actually just walk through it in a backwards way. So I'm going to make an itemized list and then I'm going to get rid of it for us, because that was us thinking about the problem backwards. Okay, here we go. For me to answer the question to find the distance, I need to know both endpoints. I know point A, I need to know point B. So I need to find B. Well, how can I find B? B is at the point of intersection between AB and the red line. That means I need to find a point of intersection. That means I need to solve a system. Well, for me to solve a system, that means I need my two equations, which means I need to find or build the equation of AB. Okay, what information do I need to build the equation of a line? I need slope and a point. And since I know that AB is perpendicular, I have both of those properties. Okay, all I'm going to do now is deal with the green, but backwards. If I find the equation of AB, I can then build the system and solve it. That'll give me the location of point B, and I can now find my distance. Okay, I'm getting rid of all of that stuff. Here we go. So the first thing I'm going to do is I'm going to build the equation of AB. And so to build that, I need point and a slope. Well, I'm going to sub my slope and point A into my slope coordinate formula. Now, I like using my slope coordinate formula other than y equals mx plus b, because then if I have fractions in my slope, I'm going to eliminate my fractions right away. That is, if I take a look at that equation, I'm going to put it in a useful form. That means I'm going to multiply out all my denominators. So I can multiply my 2 out to the right side, multiply my my x plus 6 up to the left side. So I'm going to multiply that by my negative 1. Now I can put this equation in a useful form. For me, that might be standard form. So there is my x and my y on the same side, my constant on the other. There we go. I like that. And that's all I needed, because there's equation 2. And if we look on the screen, you have equation 1 up in the top right side. Equation of the line was given. We've now built the equation for the orange line. If you want confirmation, rearrange that equation of a line into slope-intercept, and you can see your information. But I'm interested in finding point B. So to find point B, and I'm just going to come up here to the right, I need to solve my system. I can use substitution right away. Because equation 1 was given with y isolated, I could now sub 1 into 2. So I'm going to take equation 2. Wherever I see my y, I know I can replace it with what it's equal to. I can now solve that equation. And wow, do I get a nice, neat solution of 2. Well, there's my x value. I now need to sub x equals 2 back into one of my originals, and I'll sub that back into 1 because y is already isolated. That's going to get me a 4 minus 1, and I get a y value of 3. I just found that the location of B was at 2, 3. Now, I want to come back for a moment to something I said at the very beginning as I'm making this picture just a little smaller. I talked to you about the accuracy of your diagram. Because I took a little bit of care in my diagram, now when I found the coordinates of my point of intersection, they should be a little more accurate. And if we take a peek, you know what? That seems like a reasonable location. 2, 3, that's not too bad. Actually, I might chalk that up as that might be the best diagram I've ever drawn, at least in terms of accuracy. So, because I put in some time at the beginning, I get a little extra confirmation with my solution to my system. What I mean by that is, had I made a mechanical mistake in there and all of a sudden I found that the coordinates of point B were at -4, -2, you better bet that I am second guessing. I don't think I have the right B. Let me go back and look for a mistake. Okay. I've now come up with the value for B. I now need to come up with the length of the line segment. How far is it from A to B? So I am just going to come up on that right side. For me to go through now and find the length of AB, well, I can just use my Pythagorean theorem or my length of a line segment, however you want to choose that. On my diagram, I can see that I'm looking for the hypotenuse, so I've got to take my square root. My vertical side is going to be 7 minus 3, so it's 4 units long. So I need my 4 squared in my Pythagorean theorem. My horizontal side is going to be 6 units plus another 2, which gets me 8 units. And so I can just use Pythagorean theorem, or as I mentioned, you may have used your length of a line segment formula, you know, your x2 minus x1 squared plus your y2. That's totally fine. I can now calculate. And if I go to reduce that, then I get a 4 times a 20 and a 4 times a 5. I know that that whole thing will reduce to 4 root 5. There we go. That is a pretty big problem. And you can see that in that one problem, we use so many of our skills from our analytic geometry units. Dealing with perpendicular line segments, so therefore our slopes, building the equation of a line in orange, solving a system in blue, length of a line segment in green. That is a very typical problem for us to be able to go through. Okay, I want to talk about one more problem dealing with point to a line, but this one's going to be a little different. So let's take a look at the problem that I've given you, and this is our last problem for today. I want you to find the distance from 3, -5 to the line segment from that to that. So you may notice that this problem is a little bit different. I've asked you to come up with the distance from a point to a line segment, not a distance from a point to a line. Okay, that is a difference for us. Okay, is it a key difference? Well, if I was to go through and draw a quick sketch again, then I could go through and put on my information as accurately as possible. I'm looking from the point 3, -5, so I'm going to go to the right a bit and then down a bit. You'll notice that that point doesn't have a label. So my suggestion to you would be give it a label. I'll call it point A. Now I'm going to put on my other points. They don't have labels either. So maybe I'm going to call that first point point B and that first point point C. Like, if that problem you saw in purple was written as a test question, slide in little labels directly in the question. So now you have the means to be able to talk about it a little clearer. Okay, I'm going to do my best to be as accurate as I can be. I have to go to the right a lot and up a little bit. There is point B. Sorry, left a lot and up a bit. And then I have to go to point C, which is over even more and up a little bit more. And there is my diagram. Now I need to put on my line segment, so I'm going to take out my straight edge, and I'm going to go through, and I'm going to connect those 2 points, and there is the problem. Now, for us to go through and deal with the distance from that point to that line segment, we should be good again to be able to examine that what we are looking for is the perpendicular distance. So you would be coming up with what is the length from A, and then again, I don't have another label on there. Well, I've already used up B and C, so let me call that point D. There, that's what the problem was asking. Now, I think you should be good to try this problem on your own. But before you do, let's have a little conversation about something that may arise. Okay, again on your screen you see 2 sets of axes. But there is a situation that could arise when we deal with line segments. That is, distance from a point to a line segment. Now, look on the left set of axes, and you'll see our good old point to a line. But if I were to go through and start erasing those arrows, and now I said, there's my line segment, are we good that we could do the exact same thing? Yes, and I'm just going to do it quickly, but we would be looking for something perpendicular. You could find another point. You could go through and figure out that distance. However, what happens if we get something that looks very similar? That is, you have point P, and now when you are asked to come up with the distance from that point to a line segment, your line segment is like that. Well, now what do you do? Now, if we were to take a look at how we could draw a line segment from point P to my red line segment, you're going to notice you never hit it in a perpendicular way. That is, if we know that the distance from any point to a line segment or a line is always the perpendicular distance, then we have to get a perpendicular distance. And so if we were to take a look at that now, anything that would be perpendicular would have to kind of carry through in that fashion. And you'll notice that that distance that I just put on in orange doesn't even take me to my line segment. So, what would you deal with then? So, let me examine this in a bit of a backwards way and see if this can help you out. Really what I'm talking about when we say to a line segment is we have this perpendicular, right? This perpendicular range. Now, we look at that red, and we could calculate our slope of that red because we would know the line segments, the endpoints. Really what you end up getting then is almost like this area, this field. And anywhere within that field is where point P has to lie for us to use the perpendicular distance. Really, that's what that means. That once point P lies outside that distance, lies outside that field, then if we were to ask, hey, what's the distance from point P to that line segment? Really all you would do is you would figure out the distance to the nearest endpoint. So if I asked you what was the distance from point P to the line segment, and I'll even put on some labels for us just to help our conversation, then for you to come up with that distance, since point P is outside that perpendicular field, The distance from point P to line segment AB is the length of AP. That only when it's within that field, do we actually deal with a situation like the left diagram. You will notice one perpendicular, another perpendicular. Point P lies within that range. So be aware of that in some quirky situations, perhaps, that we may just be measuring point P to an endpoint. Otherwise, we know it's a perpendicular distance, and you should be good with that process. So let's jump back to problem 2. Well, now you take a look at problem 2, and you'll notice that point A lies between your endpoints. It is that perpendicular distance. We should be good to be able to solve this problem. So what I would love you to do is to try to solve this one on your own now. You see a fully labeled diagram. Let's try to take that and work our way through all of those analytic geometry skills and see if we can come up with the distance from point A to BC. Okay, pause the video now, give it a shot. Okay, we are back. So for us to go through and deal with this, we're going to have to find the coordinates of point D, which means we're going to have to solve a system. Unfortunately, we need to build 2 equations. So my suggestion to you would be use little headings. What I'm going to do is, first off, I'm going to try to build the equation of BC. That's what I'm looking for. I know to build the equation of any line, I need point and slope. Well, I have point. I actually have 2 of them, both B and C, but I don't have the slope. However, I can calculate slope. So the first thing I'm going to do is I'm going to find the slope of BC. And this is going to be me dealing with rise over run. I notice that I went up 2 for a rise, and my run was 14. That's going to give me a slope of 1/7 when I reduce. And now I can take that slope and I can use one of my points and I can build the equation of BC. So I'm going to now take my slope, and I think I would use point C just because there's no negative coordinates. So when I sub that into my slope coordinate formula, I don't have to worry about making any silly sign mistakes. Okay, I can multiply that out. And now I can put that in standard form. Now, I don't know whether standard form is the best form of this equation for me, but I'm going to put it in standard form just until I can make a decision on that. Okay, I now have the equation of BC. Nice. I now need to build the equation of AD. So what I'm going to do is I'm going to build another little heading. I know that the slope of BC was 1/7. I calculated that. What I also know then is that the slope of AD is perpendicular. So I know that the slope of AD has to be the negative reciprocal of 1/7, or -7. I need slope and a point. I have the coordinates of point A, so I'm going to use my slope of -7 and my coordinate of point A, and I'm going to sub those into my slope coordinate formula. Well, now I can go ahead and I can put that in a useful form. And now I'm getting to a point where I'm going, okay, I'm going to have to solve a system. I could generically write this in standard form and say 7x plus y equals 16. But then I'll notice pretty quickly that's not going to be a nice system for me to solve. What I mean by that is if I want to use elimination, I'm going to have to multiply an equation by something. If I want to use substitution, I'm going to have to rearrange. So my suggestion to you would be, as you're starting to rearrange the equation now, when you're trying to make that decision, do I go standard form? Do I go slope-intercept form? It might be useful for you to go through and change that and write it into slope-intercept form, because that way your y will be all by itself and you can now sub it into the other equation. Okay, there's my equation 1, there's my equation 2. I am now going to solve for d, or find d, by solving my system. Okay, I need to slide this up on my screen. So I am now going to find the location of d. And I'm going to do that by subbing equation 2 into equation 1. I have now isolated for my y. I can now sub what it is into my equation 1. Of course, had you taken equation 1 and isolated your x, you could have subbed that into equation 2. Either way is good. Okay, I now have my equation for x. Now it's just some algebraic work, making sure we're not making any silly mechanical mistakes. 7 times 16 is a 70 and a 42. So a 70 and a 42 is 116, yikes, 112. That gets me a 50x is equal to, now I need to take that off, and that's going to get me a 92. I can now reduce that fraction and get 46 over 25. A nice, neat x-coordinate. Ugh, that's ugly. Okay, I can now take my x value of 46 over 25 and sub it back in. Now, for some of us, because we got this value of 46 over 25, we might go, oh, that's ugly. I must have made a mistake. Don't let getting an ugly number make you feel like you made a mistake. Trust it. Not all your answers work out to nice, neat things. Look at your diagram. Look at your sketch. Is it reasonable that your x could be 46/25? Yeah, that's a high 1 point something. That's reasonable. Look at the location of D. So trust yourself. Now I'm going to go ahead and I'm going to plug that in. And I'm probably going to sub it back into 2 because the y is already isolated. Well, that's going to get me y equals -7 times 46 over 25. Oh, this is going to get ugly. Okay, I'm going to get something nice and big. So I'm going to go ahead and I'm going to calculate that 46. I would take a first look, though. My 7 does not reduce with that 25, and we should always be looking to reduce that thing. So since it doesn't, now I'm going to multiply my 7 in. That's going to get me a -322/25. And right now, I can see I'm going to need to get a common denominator. So why don't I already change 16 into 25ths? That's going to get me 425ths. I now have my common denominator, so I can go ahead and put those things together, and that's going to get me a value of 78/25. Now, my denominator is 25. It's only made up of 5s. I see that there are no 5s in 78, so therefore, I know that point D is fully reduced at 46/25, 78/25. Oh, this has not gotten any neater. So back on my diagram, I'm just going to label the coordinates of point D. I found that D was at 46/25 and 78/25. Now, I take a look at that solution. Again, don't doubt yourself, but check. So that would be a 1 point something and a 3 point something. And that makes sense. Look at the location. Because I was trying to be as accurate as I could be when I made my picture, that fits my diagram. That makes me super confident. Now, I just need to come up with the length of AD. So I am going to wrap back around. I'll shrink this down for 1 second, but I am going to wrap back around. And now I'm going to actually answer the question that was asked. I'm going to find the distance from A to D. So A to D is now big ugly square root of my right triangle. Well, my right triangle now gets pretty ugly. Okay, my vertical distance is going to have to be from 78/25 all the way down to -5, which means I need to take that distance of 78/25 and add on down to 5. And then my horizontal distance is going to be from 46/25 over to 3. So I need to find the difference of 3 to 46/25. Okay, a ton of common denominators, a ton of ugliness. Let me show you a little trick as you work your way through. Okay, first off, we're going to have to get common denominators on the inside of our brackets. Now, for me to calculate that, I want you to watch what I'm going to write down. I'm going to now change my 5 into 25ths, so that is 125 of them. And I'm going to do the same thing on the other, change my 3 into 25ths. There is me using my Pythagorean theorem. There is me getting common denominators. What I now need to do is simplify the tops of both of those fractions. So I am going to take my 78 and I'm going to add to that a 125. So that is going to get me 203 25ths. And then on my other fraction, I need to take a 75 and minus that 46. So there is a 29 25ths. Okay, we're still working on it. Yikes, this is ugly. I'm going to just slide that up to make a little bit more room. When I go to calculate that, I now need to square all parts of your fractions. Okay, you're going to watch the way I write this down. I can see that when I go through and I square the top and the bottom of both fractions, I'm going to have a common denominator of 25 squared. I'm not even going to calculate what 25 squared is. And you'll see why in a second. Okay, on top, I now need to square my 203. Well, that's going to give me a nice, big, nice, and neat 41,209. Yes, I'm using a calculator on this. That's not me pulling that out of my head. Now I need to square my 29, and that's going to get me an 841. Okay, keep following BEDMAS. If I take my 841 and now I add to that my 41,209, then that is going to give me a 42,050 over 25 squared. Okay, you may be asking, hey, why are you still not calculating 25 squared? Because look what my next operation is going to ask me to do. I'm either going to reduce that fraction on the inside, or I'm going to take the square root of 25 squared. Okay, I am running out of all sorts of room, so I am going to wrap all the way around here so I can continue my work. Well, I'm now going to calculate, or simplify, the square root of 42,050 because I can take the square root of 25 squared and it's just a 25. That it wasn't worth it for me to ever calculate my 25 squared, write down 625 every time, and then keep going through just to now take the square root of 625 and get back to 20. Maybe you can see what I'm talking about in that orange. Okay, I would love it if when I took the square root of 42,050, I got a whole number, but I don't. So that means I am doing a nice big factor tree. I'm going to just shrink my marker a little bit because this could take a while. So what I'm looking for is perfect squares. Well, my answer ends in a 50. So I know then that 25 is going to go into that evenly, and 25 is a perfect square. So that's not a bad number to divide out from the very beginning. Well, now I've got my 1682. I notice that if I divide that by 4, I get a decimal. So the most I can divide in terms of that even number would be a 2, but at least that would allow me to shrink it down a little bit. That's going to get me 2 times 841. Well, hey, if I go back into my work, I notice that 841 is 29. So that is a 29 times a 29. And I've now figured out my factor tree to be able to reduce that to lowest terms. So maybe I'm going to just sneak in this line in here if it helps you a little bit. I can take the square root of my 25. That's a 5, so that's gone. I can take my square root of 841. That was a 29, so that's gone. The only thing I couldn't take the root of was the 2. It's left in there. However, I'm thinking that a lot of us would be okay just to go straight to my 5 times my 29, and that was a 145 root 2. But now you see with your whole numbers, you have a common factor of 5 in there. And so if you take your 145 and divide it by 5, you get back to your 29. And take your 25 and divide it by 5, you get back to 5. Holy cow. Okay, that was messy. But we finally answered the question. What is the distance from point A to that line segment? All the way at the end, it's 29 root 2 fifths is our distance. Okay, that was a huge problem for us. But again, look at all the parts in there. We should be comfortable to deal with all those parts. You had to go through and build some equations of lines, no problem. You had to solve a system, shouldn't be a problem. You had to find the length of a line segment, shouldn't be a problem, even though the numbers got really ugly. Take your time, map out your process, have confidence in your skills. Okay, 2 problems for today with a little bit of a discussion on some theory about how we measure distances from points to lines. Your job, jump in and get as much practice as you can and make this process automatic. Good luck.